Hi, my name is Carlos Aguilar Melchor. I'm going to present some joint work with Joris Barrière, Laurent Fous, and Marc-Olivier Kiljian. So I'm going to first introduce the context of our work and then present a small performance evaluation and some usage guidelines for our project. So let's start with the introduction. We are interested on privacy information retrieval, or PIR or PIR, the name changes from person to person. And the idea, well, you already have understood it on the previous talk. It's about hiding a user choice. So there is a database, and the user wants to hide his access pattern. And the idea is that it's the choice that is private, not the data. The database can be public, can be DNS records, public keys, movies, whatever. So it's the choice of the user that is private. So it's very simple to understand that on a trivial non-private protocol, a user who would want an element from a database of index I can tell it just to the database, and the database has just to send the element back. So it's simple, it's fast, and it's non-private. If you want to make something private, it's very easy. You can do something that is trivial. You can ask to get the whole database and then choose locally which element you're interested on. And that's trivial, but some common characteristics to many peer protocols appear already. All the database is processed, and the processing is sending the database over the wire. So the processing speed for the database is the bandwidth globally. So it can be from 10 megabits to 1 gigabit today. And the database is processed by being sent to the client. So if you don't want to send the whole database, you have some alternatives. You can use an anonymity system. You can relax the notion of privacy with respect to downloading the full database. Or if you want to have roughly the same privacy as downloading the full database, you can use an information theoretic PIR protocol in which the basic idea is to have replicas, some of them not colluding together against the user. And then, I won't explain how, but you can get protocols that are cheap in communication, cheap in computation, and that provide information theoretic security for hiding your choice, as long as there isn't a collusion among the replicas, or a large enough collusion. The other option you have, if you don't want to have replicas for the database because you cannot afford that, for example, or you cannot afford collusion assumptions, then you can do it with a single database without replicas. And the idea is that your security will rely on the security of a crypto system, and then you get what we call computationally private information retrieval. And the drawback of these approaches, of course, is that you will have a higher computation or communication costs and only computational security. Okay. That's the area in which we have contributed. We propose a XPIR protocol, and a notable work is the one of Devet and Goldberg 2 years ago in this conference, in which they propose to combine both protocols. And the basic idea is that if you can afford replication, you can use it together. You can use ATPIR together with computationally private information retrieval. So you make ITPIR do most of the work, and then at the end you do a little bit of CPIR for smaller subdatabases, so that you get, for most of the work, a fast protocol. And if there is a collusion among the replicas, then the CPIR protects you a little bit. So there is a more graceful degradation of privacy when there is a collusion. So if you can afford replicas, I think this is the way to go. Ideally, as the XPIR building block, the most performant today is XPIR. So it would be combining this construction with XPIR, I think, the best solution. If you cannot afford replicas, well, XPIR provides a non-replicated system that is quite performant already. Okay, so let's talk about XPIR protocols and explain why they are they need some work to be improved. So the basic idea on XPIR protocols is that the user chooses an element by an index, And then he generates a set of ciphertexts which are under an homomorphic encryption scheme. And if the encryption scheme has a given security property, namely its indistinguishability against chosen plain text attacks, all the queries look alike. Whatever the index chosen is, all the queries look alike to the server, and the server will do always the same computation. He will combine database elements with query elements and obtain a result, which in fact is a set of ciphertexts. And when the client gets back this result, he just has to decrypt the ciphertext to get the element he wanted. So as in a trivial peer protocol, you see that the whole database is processed, but instead of being sent, there is a mathematical computation that is done that allows to have a more compact result that is sent. So you have better communication, but higher computational costs. So the basic constructions to get computationally private information retrieval protocols are due to J.P. Stern and Helger Limma. So Stern proposed a generic construction that transformed an additively homomorphic encryption into a XPIR protocol. And Limma proposed an improvement which allows to have much better communication complexity if you use it with a specific homomorphic encryption scheme, which is due to Dambriat and Durick. It's a generalization of Payer's cryptosystem. So such construction is very efficient from a communication point of view. Even for huge databases, like 10 to the power 15 elements, you have a small query, and you have a not so large expansion factor. For smaller databases, you will have an expansion factor that will be roughly 2, and it grows slowly with the database size. However, from the computational cost point of view, it's almost prohibitive to generate the reply. For every bit on the database, you have to compute a 2048-bit modular multiplication. So that's very, very expensive. So that's roughly 10,000 cycles on my computer for each bit on the database. And then my quad-core computer can do something like 0.7 million such operations per second. And a high-end Xeon 14-core laptop can do a few megabits per second. So the database is processed at a throughput of a few megabits per second. So if it's 1 gigabit large, you will need 1,000 seconds to generate the reply. In fact, those processing speed is lower than the processing speed of trivial peer, in which the processing speed is the connection speed, and most connection speeds are above this. So in practice, it's more efficient to do a trivial peer than the classic computationally private information retrieval protocol. So as implementing Stern's construction with classic homomorphic encryption schemes was very slow, some alternatives were proposed, and they were based on somewhat ad hoc problems. So they were much faster than constructions with Payet, but they are both broken. Yet, they are constantly being cited as the reference for computational peer performance, and it's those constructions that is used in all the applications of computational private information retrieval nowadays. So, what are the lessons learned since these proposals? Well, you have to use standard crypto systems, standard parameters, okay? And today, probably the best choice is to use lattice-based cryptography, and more precisely, the ring LWE-based lattice-based cryptography. So this leads us to our proposal, XPIR. So in our proposal, we use lattice-based cryptography, which in practice, I won't enter into too many details, allows you to replace modular exponentiations that are done with Payet, and you can replace them with matrix or polynomial multiplications with coefficients that fit into hardware registers, so you can do native operations very fast to compute these matrix and polynomial multiplications. So doing a just trivial implementation of a lattice-based crypto system to replace Payet, you get a quite nice speed up. You go from, on my computer, from roughly 10K cycles for Payet to 800 cycles. And one of the contributions of our work has been to do a fast polynomial and modular arithmetic kernel which in fact has been extended to do some more things, and now it's an independent project called NFLlib. And it does polynomial multiplications by pointwise point representation, and it has very fast transformations, and it uses specific moduli to have a very fast modular operations. With these changes, which I cannot describe in the time given, we can go down from 800 cycles per bit of the naive implementation to 2 cycles per bit. And if you can do some precomputation, namely applying the FFT-like operation before the queries are done, then you drop down to 0.5 cycles per bit on the database. So you pass from 10,000 to 0.5, so it's a quite change of a situation for computational performance. Okay, there are some bad news. Communication performance for lattice-based cryptography is worse than for classic PAYE-like cryptography. A PAYE ciphertext is 2 kilobit long, and the expansion factor of encryption is below 2. Okay? So you can easily, it's 2, but you can lower it easily. In lattice-based cryptography, ciphertexts are between 128 kilobits and 1 megabit long. So we have almost 2 to 3 orders of magnitude of difference. And the expansion factor is also larger. But the good news is that you have to pay a little bit more of communication, yet you are much more efficient than a trivial peer protocol, and you have very, very important processing throughput. So if you use parameters for 90-bit security, you get 25 gigabits per second processing of database. So that's quite a lot compared to 1 megabit per second for PAYE. And if you want higher security, 256-bit security, you drop only to 15 gigabits per second. That's a characteristic of lattice-based cryptography. When security scales up, performance lowers very little. If you have been able to do the preprocessing before the peer query, if your database is very dynamic and you cannot do that, then you will have a bottleneck on the preprocessing, and you will answer the queries processing the database at 4 gigabits per second, which is already faster than almost any connection, realistic connection. For example, you can do things that weren't possible with PIR before. You can take a 1,000 movie database. You can watch a movie on real time on HD, and you will only use 2% of the server CPU. Okay, so a CPU can handle 40 clients watching HD movies on a private database. So you have the project on GitHub. It's self-configurable. You don't need to be an expert on crypto or on PIR to use it. It's based on a standard crypto system, can reach up to 156 bits of security, and has no word assumptions. So how to use it? Very easy. You clone it with Git. You build it with CMake. You have a client and server application, an auto optimizer that chooses the parameters for you. That's why XPIR is for everyone. Okay. And an API if you're an advanced user to do your own PIR applications. As a client and server application is very simple. You drop some files on a directory, you run the server on the client, you choose the file, then the client runs a self-optimization for the database and connection, and you recover the result of the file. The optimizer basically measures bandwidth, the performance of each operation on the client and on the server, and then explore potential parameters to optimize a target function, round trip time, amount of data exchanged, CPU and data exchanger to make some sort of cloud price. And then you have a library in which you can easily build the crypto objects. We have a no crypto, which is for trivial peer. We have a PIR crypto system, and we have a ring LWE crypto system. Then you build the PIR basic objects. You can have databases from a directory, from a file that is split, or from random databases to generate fake large databases. Then you have the possibility to import the database to do preprocessing simply, and then functions to generate a query, generate a reply, and extract a reply. So that's all. We are integrating to XPIR fully homomorphic encryption. We are integrating better handling of sparse databases. We are using it for applications on genomic research. We are building a sniffer that when you discover it, you don't know what it was sniffing, to show that PIR can be quite dangerous too. And we are working on several improvements, and if you have ideas of application, we are open for collaborations. Thank you.